Um, what I want us to have a reflection on the type of regression that we've done before. I could remember in the beginning of the semester, I introduced you to linear regression. And of course, we apply linear regression in a situation whereby we're trying to characterize relationship between two or more variables in such a way that we actually want to predict response from the predictors. And of course, the nature of the response is quantitative. Okay. From there, we move to a situation whereby the response variable is categorical. And of course, when the response variable is categorical, I actually demonstrated to you that using ordinary linear regression may be out of place. Of course, using ordinary linear regression may be out of play because the response variable have a restricted bound. The response variable have a restricted bound in a situation whereby the response variable is categorical, because when you try to use linear regression, whatever prediction you make with that will not make sense. Okay. Now, from there, we actually move to a situation whereby we're trying to characterize a relationship between two categorical variables, which I call the analysis of categorical variables. I think I walk you through that, where we're able to use a chi-square test of association to investigate that. And of course, today, we got off in a situation whereby we are still trying to look at the relationship. Okay, we're trying to study relationship between two variables, but the response variable this time around is a count. Okay, the response variable is a count. Okay, now if the response variable is a count in such a way that these counts are non-negative integrals. Okay, they are non-negative integrals, and of course, they represent the number of occurrences in a fixed interval. I'm going to say that again. The number of occurrences in a fixed interval. And of course, the occurrence of events in a fixed interval, which is more or less likely to be a real event. And I'm actually going to give you an example of such. Okay, where the response variable is still quantitative in nature, but only that is a count data. And the question now remains, what do we mean by count data? The count data are, are non-negative integers values. Okay, we're referring to the number of occurrences in a fixed interval. Okay, an example of that, we may actually want to know the number of criminal cases before a criminal court per year. That's an example of a count data. I'm going to say that again. The number of criminal cases, okay, before a criminal court per year is an example of count data. Of course, we don't expect the number of that to be negative, and we don't expect to be continuous. We actually expect it to be discrete. Okay, so situation whereby the response variable is strictly discrete. Okay, and you are trying to look at the relationship between that and some predictors. Of course, we're going to use Poisson regression model. I'm going to give you another example under count data. Another example, we may want to talk about the number of crime cases on campus per year. That's another example. And we may also want to know the number of jump. Okay, you may want to know the number of jumps in stock returns per day. Okay, the number of jump in stock returns per day could also be seen as a count data. We may also want to talk about the number of accidents that will occur in the city of Chicago in a week, or the city of Minneapolis, or city of Philadelphia, or the city of San Francisco, or in a particular city in a week. That's a count data. Okay. Now we may also want to know, for instance, um, you know, there in a recently concluded presidential election in the United States of America, of course, we see a situation whereby a certain political party has alleged of a fraudulent, practices during the election. Okay, so of course, with any country that have election integrity, the probability that that will occur, you know, may be very, very small. But you know what? The fact that the occurrence of an event, the number of occurrence of an event in an interval should will be very, very small, does not mean that it cannot occur. Okay, so another example, you could talk about the number of a doctor visits per year. How many times do you visit a doctor in a year? Visiting a doctor in a year may not be predetermined. These are these are on predetermined events, because what happened for you to visit a doctor, is a random event. Okay, so there are so many examples of account data that we can actually talk about. Another example that I actually want to talk about is, if you take a look at the if maybe you visit a grocery store, the number of customers that are queuing in front of you. Okay, the number of customers that are queuing in front of you. Okay, that follow a Poisson process. Okay, so those are the example of account data that I actually talk about. Okay, so I'm going to go to page 2 right now. And what we have in overview, we actually want to have a way to model counts. Okay, we want to have a way to model counts. And why is it that the the regression analysis that we've done before, why does it fail to model counts? You remember when we're talking, the reason why we go from ordinary linear regression to logistic regression is because of the fact that the nature of the response variable is categorical, and because you know uh, that have a restricted bound. The response variable actually have a restricted uh, bound, and because of that, give me 1 second. So because it has a restricted bound, okay, and because of that, uh, we I'm using ordinary linear regression to model that is actually uh, going to be out of bound. The prediction we actually going to have, we go out of bound, and that is the reason why we go for logistic regression. Okay, but you know what? Why is it that we cannot also use ordinary linear regression here to model counts? Because when there's going to be, number one, there's going to be violation of assumption of normality, because the probability distribution of counts is not normal. Okay, the probability distribution of counts is observed to be skewed. Okay, that is number one violation. Number two violation of the reason why we cannot use the linear regression to model count is because of the fact that when we use it to model count, there's possibility when we're making prediction with a model, we actually, there's possibility of having a negative values. Okay, there's possibility of having a negative values, a negative integer values. And you know what? The number of occurrences that we talk about in a fixed interval cannot be negative. Okay, okay. So the number of occurrences in a fixed interval cannot be negative. At least it's actually going to be zero. Okay, so because of that, the appropriate statistical model that can actually be used to model count is Poisson. Okay. So, but if we are looking at the count relatively to, maybe if you are looking, if you are trying to model count data as a function of covariate, then we're going to be talking about Poisson regression model. Okay. And of course, we also use Poisson regression to analyze contingency tables. Okay. You remember the other time when we're dealing with the analysis of categorical variable, we always have what we call a cross tabulation of the two variables. So Poisson regression can also be used in that regard. Or can you guys confirm if you guys are still hearing me? Okay, thanks for confirming that. Okay, so I'm actually going to go to page 3 right now. And you know what? This material, we actually going to use this material for this week. Okay, I'm confirming that to you. Okay, so we just discussed page 2 right now, and I'm actually going to take you to page 3, okay, of the material. Now, on the page 3 of the material, we want to focus on the modeling count, 1. And of course, I've given you the number, I've given you examples, okay, and these are other additional example of count data, okay, number of traffic accident per day, the mortality count in a given neighborhood per week. Okay, so that's a count data. Okay, number of calls in a concert hall per minute. Okay, that's a count data. The number of customers arriving in a shop daily. That's another count data. Okay, in each of these data, you don't expect to have a negative, and not only that, you don't expect to have a continuous data. A continuous data means probably 7.5, 8.5. We can never have 10.5 number of accidents, as the example that I just showcased right now is pure, is strictly discrete. Okay, it's strictly discrete. Okay, so that is page 3 of the material, and I'm actually going to go to page 4 right now. Okay, so what do we actually want to do in page 4? Page 4, the modeling can't actually continue. Okay, uh, like I said, they can't show up in all kinds of scenarios in our everyday life. Okay, where we talk about counts in sports, in disease. Okay, in a football game. Of course, the football game is actually played in an in a fixed interval of time. What is the number of goals scored? Okay, that's a count data. Okay, we may also want to talk about in public health. Okay, count data are particularly important in measuring disease rates. Okay, so what I'm trying to tell you right now, if you want to measure disease rates or you want to measure incidence rates, okay, you have to look beyond the conventional ordinary linear regression we did and the logistic regression. Okay, you have to look beyond them. Okay, you got to use a Poisson regression model. Okay, if you actually want to handle incidence rate. Okay, now modeling, and that was why I said modeling can give us a framework in which to estimate disease incidence. Okay, just like right now, we're in the middle of pandemic, and the effort of every country is to be able to ascertain the true value of the incidence, the disease rate, and therefore the most appropriate regression model that can actually be used that will allow us to measure association between incidence rate and risk factors of interest. Like I said, after adjusting for other related, I said we can only use Poisson regression model if we really want to model counts, okay, as a function of covariate. What we mean by covariate, the covariate are the factors that could be responsible for a particular count that we're talking about. Okay. For instance, you go to a grocery store and then you queue up, okay, behind some customers. Okay. Now the number of customers ahead of you, okay, the number of customers are ahead of you at that time period, it's a count data. Okay. Now, the number of customers ahead of you could be 0, it could be 1, it could be 2, and so on like that. And you know what? There are some potential factors that could actually explain why you have a lot of people ahead of you. And one of the factors may actually be maybe the store actually have a discounted price on a good number of items. Of course, you know how consumer behave. Okay, a lot of people will want to buy more things at a lower price. Okay, that is the theory of consumer behavior. Another factor that will be responsible why you have a lot of people ahead of you when you go to grocery store, maybe it's an holiday season. Okay, I could remember on the Black Friday, I actually went to a Best Buy, to buy items. And I realized a lot of customers are ahead of me. So I got to wait. Okay. And then, of course, what actually responsible for that may be the fact that, okay, that's our holiday season. And of course, the Black Friday, is actually, a day where customers actually offer discount, where the sellers of products actually offer certain discounts for their customers. Okay, so can you guys confirm if you guys are still hearing me clearly? Can you guys see hear me clearly? Okay, so I'm gonna go to page 5 right now. I'm gonna go to page 5 right now. Give me 1 second. I'm actually gonna go to page 5. Okay, so I'm on page 5 now. A whole new model to deal with counts. Like I said, the use of Poisson regression model will be used to model counts as a function of a risk factors. Okay, and you know what? Uh, uh, the one we've talked about before, the models, the regression model we talked about before, I could remember we've talked about linear regression model, and of course, the assumptions of the line, the error in linear regression model is normal. Okay, and that very assumption will be violated. Okay, when you are dealing with the count data. Okay, and that is the reason why linear regression cannot be used to model count data. Okay, that's one of the reasons. Now, what about logistic regression that we've done before? The logistic regression we've done before has a binomial distributed errors. What do I mean by binomial distributed error? Because the response variable, okay, is categorical for you to use logistic regression. And of course, when the response variable is categorical, it means it could have a two nature. Possible nature is actually going to be 2, also which is binary. And of course, the probability distribution of the binary data is binomial. Therefore, we expect the probability distribution of the errors in binomial, in that to be binomial, and that is the reason why, uh, we cannot use a linear regression for a situation where logistic regression applies. And of course, where logistic regression applies, we cannot use a Poisson regression. And why is it that we cannot use a Poisson regression? Because the count that we're talking about, it is not 0 and 1. Okay, in logistic regression, the response variable is actually 0 and 1. It's either you have this or that. Okay, but in the case of a count, it is not like that. Of course, the count could be 0. Okay, it could be 10, it could be 5, it could be whatever. Okay, so because of that, the nature of the count, it is not 0 and 1, and therefore logistic regression is not appropriate. And of course, the count data are discrete. Okay, if you take a look at the example that I cited the other time, the number of cases of COVID, you can't say 10.5 people have COVID. No, it has to be discrete. Okay, the number of accidents in a year, or probably in a city, is discrete in nature. Okay, you can't say 10.5 accidents. Okay, the number of children born to a couple is discrete as well. The number of goals scored in a match in a football game is also discrete. Okay, so therefore, when you are talking, we know count are discrete. Okay, they are not continuous, and that is the reason why the linear regression and the logistic regression is actually going to be deemed inappropriate. Okay, and another thing that you know uh, the linear regression and the logistic regression we have discussed so far cannot be used to model count data is because count data are typically right skewed. Typically right skewed in the sense that they are not, if a particular data set are not normally distributed, of course it means there's a skewness. Okay, skewness is a departure of data from normality. Okay, and when the data is skewed, it's either it is skewed to the right or to the left. Okay, the count data actually have history of being skewed to the right. Okay, so I think I've stated the reason why you know why the count data do not actually follow any of the distribution that I've actually highlighted. Okay, so this is page 5. I'm actually going to go to page 6 right now. Okay, so we are on page 6 right now. We are still on a whole new model to deal with counts, which is the Poisson regression model. I've been able to justify the reason why we are not able to use the conventional regression we've discussed before, the linear regression and the logistic regression. I think I've justified that. And you know what? What do we look up to in modeling counts? Okay, if we want to model counts, what do we actually look up to? Okay, we look because what we look up to in modeling counts is actually we are typically interested in modeling incidence rates, of course, which means the conventional linear regression and the logistic regression cannot actually handle incidence rate. Okay, if you are interested in incidence rate, okay, of certain characteristics of interest, of course, I will advise that you should look beyond uh, linear regression and logistic regression, but you focus on the Poisson regression. Okay, because you know the strategy that we applied in the conventional regression that we have done, the linear regression actually focus on the expected values and the expected increases. Okay, and of course in the logistic regression, that we talk about the log odds, or the log ratio, where we are trying to investigate the incidence of a particular occurrence based on certain risk factors. But situation whereby the interest is now on the incidence rate or incident ratio, okay? Because when you are trying to characterize, when you are trying to look at the number of occurrences in a fixed interval of time, of course the incidence rate is actually going to surface, and therefore since we're typically interested in the incidence rate of the characteristics of interest, of course we got to talk about model counts. Can you guys confirm if you guys are still hearing me? Okay, now the Poisson regression will actually provide us a framework to handle counts properly. Okay, if you use any other regression model, you are not going to get a good result. That's what I'm talking about. Okay, if you're modeling count, of course, if you want to model count as a function of covariate, as a function of certain risk factors, of course, you got to consider Poisson regression. Okay, so you got to consider Poisson regression. Okay, now that is page 6. I'm actually want to go to page 7 right now. I want to go to page 7 right now. Okay, now in page 7 right now, we have been talking about Poisson regression model. I've walked you through, why the conventional regression failed. I mean, the linear regression and the logistic regression, why they fail in modeling count data. And of course, I said the Poisson regression will actually do the job. But you know what? Uh, let's all of us look at the Poisson assumption, because every statistical model has assumption. Okay. And of course, we actually need to uh, look at this assumption, put this assumption into consideration. Otherwise, uh, you know, Poisson regression will no longer be appropriate. And that was why I said, before going to talk about Poisson regression, we're actually going to visit some concepts about Poisson distribution. Now, let me tell you this. There's a difference between Poisson regression and Poisson distribution. Okay? So because we actually want to talk about Poisson regression, because Poisson regression is actually a regression model that we use, okay, in modeling counts, okay, as a function of some potential risk factors, okay. But you know what? The underlying distribution of the error, okay, in a Poisson regression model is not going to be normal, but Poisson, okay. And that is the reason why we actually want to talk about Poisson distribution right now. Okay. Now, when we talk about Poisson distribution, one of the assumptions in the Poisson distribution is that the occurrences of a random event in an interval of time are independent. Okay. They are independent in the sense that, um, you know, when you are considering a particular interval of time, okay, the occurrence of an event, in that interval of time, because it's purely random, is an, the occurrence of any event is independent of another event. Okay, when you are talking about accidents right now, the fact that accidents occur in you know in a particular street, okay, on Monday, does not, you cannot use the occurrence of accident on Monday to predict the occurrence of accident on Tuesday, because they are independent, because they are random events. Okay, so that assumption must hold. Okay, and number two, that there's possibility of having an infinite number of occurrences of the events, within the interval. Okay, and that is the reason why we said, um, you know, when you are talking about count data, the count data is actually going to go from 0, 1, 2 up to infinity. Okay, there's possibility that you have a zero case of that within the interval. There's possibility you have one. There's possibility you even have a lot of occurrences. Okay, you remember the cases of COVID. The cases of COVID actually started, there was a time where in any country in the world, that have huge number of cases right now, we got a time where there was a zero number of cases of COVID. Okay, I'm talking about pre-COVID era. Okay, before the COVID. Okay, and before the number keep on going up. Okay, so that's an example of a count data. Okay, and then there's another possibility in an extremely small portion of the interval. The probability of more than one occurrence of the event is approximately zero. What do we mean by that? Maybe I want to, maybe for instance, probably in the city of Minneapolis or in the city of Chicago, maybe I probably want to observe the number of occurrences of an accident between 9 a.m. and 9:05. Okay, between 9 a.m. and 9:05, that's a 5-minute interval. That's a very small interval. There's possibility that um, you may not have a occurrence of an accident within the interval, within the small interval. Okay, that that doesn't mean it cannot occur. This can occur, but we're just trying to say the probability of this occurring is approximately zero. Okay, now these are assumptions of a Poisson distribution. Okay, now I want to move to page 6 right now. Give me 1 second. I'm actually going to go to page 6 right now. Okay. Uh, okay. So yeah, I think I've talked about page 6. Let me see. I think I just talked about page 7. Give me 1 second. Okay. So yep, we've talked about the absorption. Oh, okay. We're on page 8. Now we've talked about absorption of the Poisson distribution. Now let us now first look at the Poisson probability. Before we go into Poisson regression model, what we're trying to do right now, we're trying to understand the Poisson probability. The Poisson probability is the probability distribution of the count data, and which that is very, very essential. Okay, understanding that is very essential to fitting Poisson regression model. Now, take a look at this guy now. Okay, if I want to find the probability of the occurrence of an event in an interval, that is a model. That is a probability distribution. That is what we call a Poisson distribution. And of course, what is X? X is a number, the number of occurrence of events. Okay, and the number of occurrence could be 0, could be 1, could be 2, could even go forever. Okay, so which means if I want to find the probability that we're actually going to have the number of occurrence of certain event within a stipulated interval, of course, this is actually what I'm going to use. Okay. Now here, X is a count data. X here, a count data, of course, is the number of occurrence of an event within an interval. Okay. And of course, what is lambda? The lambda here is actually the expected number of occurrences in the interval. Okay. And of course, before I can use a Poisson distribution, or before I actually need to estimate my lambda, I need to know my lambda. The lambda has to be known, which is the expected number of occurrences. Okay. And of course, in Poisson distribution, the mean and variance are equal. Okay. Take a look at that. Okay. The mean and variance are equal. Now, let me tell you this. In a situation whereby the variance exceeded the mean, okay, in a situation, because we could have some situation whereby the variance could exceed the mean. When variance exceed the mean, what I'm talking about, if you're talking about a count data and the variance of a count data actually is greater than the mean, okay, then in that situation, we can no longer use Poisson regression. I'm going to say that again. The one of the assumption using Poisson regression is that the mean and variance of the count should actually be equal. Okay, in a situation whereby the variance of the count data actually exceeded the mean of the count data, that problem is what we call over dispersion. Okay, that is what we call over dispersion. Okay, and in a situation where you have over dispersion, you even though if the response variable is count, you can no longer use Poisson regression. But what can you use instead? You're actually going to use what I call negative binomial regression. Okay, let me tell you this. There are different kind of regression. Okay, but you know what? We are not going to do negative binomial regression in this course, but I'm just trying to let you know. Okay, I just try to let you know that situation whereby you are talking about count data, and we realize that there's a problem of over dispersion, because if there's a problem of over dispersion, and if you use Poisson regression model, of course, you're actually going to take a misleading decision at the end of the day. Okay, your model will be misleading, and that is the reason why you actually need to look beyond Poisson regression. In a situation where there's a problem of over dispersion, you're going to make use of negative binomial regression. Okay, and then of course I told you what we mean by over dispersion. Over dispersion means the variance of the count data is actually greater than the mean of the count data. Can you guys confirm if you guys are still hearing me clearly? Okay, so I want you to take into consideration what I just talked about right now. And you know what? The lambda that I just talked about, that I call the expected number of occurrences in the interval, can also be called rate parameter. Okay, we can call that rate parameter. We can call that intensity parameter as well. Okay, and of course, for you to be able to apply Poisson regression, the mean and variance has to be equal to that lambda. The mean and variance of the count data have to be equal to lambda. Okay, in a situation whereby the variance exceeded, the mean, of course, you have a problem of over expansion, and therefore Poisson regression is no longer appropriate. Then you got to use negative binomial regression. Okay, and then there's another violation that I'm also going to talk about before I move on. Another violation is in a situation where you have SS zeros. Okay, situation where you have SS zeros, you are not going to use Poisson regression. You are not going to use negative binomial, but you're actually going to use what we call zero inflated regression model. Now, let me give you the scenario, under which your data could have excess of zeros. Now, right now in the United States of America, there was a presidential election which has been concluded, and of course, a certain political party has alleged that the election was kind of fraudulent. And take a look at this. This particular political party has already filed a lot of so many lawsuits in court. And take a look at this. If we let's say based on my knowledge, I heard that they filed probably up to 100 cases. Okay, now if we want to know, the occurrence of victory in a week, okay, if I want to know the occurrence of victory in a week, okay, I'm referring to the Trump campaign organization. Okay, so if I consider week 1, week 2, week 3 up to week 10, okay, maybe what I'm interested in is what is the number of victories, okay, that the Trump campaign is actually going to have in a court in a particular week. Okay, of course, based on my knowledge, some cases have been thrown out, some cases, stuff like that. Maybe in week 1, we have 0. Okay, they have 0 victory. Week 2, 0 victory. Week 3, 0 victory. Week 4, 0 victory. Maybe from week 1 to week 8, they have 0 victory. And maybe week 9 and 10, and if they have victories, maybe the victory could be 10 per week, it could be 15. So that kind of data is called zero. We have excess of zeros. Okay, it's a count, but the fact that we have excess of zeros, you can no longer use Poisson regression, because of the fact that there's actually going to be a problem with the Poisson regression, and we're going to use what we call zero inflated regression. Okay, we're going to use zero inflated regression, but you know what, zero inflated regression, we are not going to do that in this course, but I'm just trying to tell you situation where you have excess of zeros. Okay, and you are still talking about count data. Okay, so this is page 9. I'm actually going to page 8. I'm actually going to page 9 right now. Okay, so on page 9, what am I trying to showcase on page 9? What I'm trying to showcase on page 9 is to tell you that the probability distribution of Poisson is non-normal. Okay, when lambda equal to 5, okay, when lambda equal to 5, and I actually use the probability distribution, what did I use to plot this? Of course, what I used to plot that is the probability of S equal to exponential raised power minus lambda raised power x over x factorial. Don't forget, S start from 0, 1, 2, and so on like that. Okay, when I assume my lambda to be 5, this is the shape. And if you take a look at this shape now, this shape is skewed. It's skewed to the right. Okay, so this is an evidence that the Poisson distribution is skewed to the right. Okay, now this is page 9 right now. I'm actually going to go to page 10 right now. Now on page 10, if you take a look at the shape that I have right now, it's looking like a normal shape because my lambda now equal to 30. Okay, now the take home here is that you know, the shape of the Poisson distribution actually depends on the lambda. Okay, when lambda equal to 5, you saw what we got the other time. And now when lambda equal to 30, take a look at the shape we're having now. The shape is looking like a normal distribution. Okay, take a look at that. Okay, so that is page 10. I'm actually going to walk you through page 11 right now. So I'm going to go to page 11 right now. Now on page 11, I want to talk about Poisson and binomial. And what do I want to talk about right here? I actually want to trace the origin. I want to trace the origin of Poisson distribution to binomial. And let me tell you something. You know, uh, if I'm trying to look at incidence rates of maybe accident, okay, or incidences of disease, it's either there's a disease or not. It's either accident occur or not. It's either there's a fraudulent case in an election or not. Okay, and of course, because of the fact that situation where n is large, the probability is going to be very, very small. The probability of getting a fraudulent case in an election for a country that has integrity, the probability is actually going to be very, very small. And you know what? When the probability is small, that doesn't mean the event of fraudulent cannot occur. Okay, so when n is large and probability of the characteristics of interest is very, very small, of course, we expect the product of NP to be equal to lambda. Okay, so which means we actually go from binomial to Poisson distribution. And of course, the moment you have a lambda, lambda is an attribute. Lambda is an intensity parameter of a Poisson distribution. Okay, so what we're trying to talk about, we use this distribution to model real events. Okay, the model count that we're talking about, the count data you are talking about is more or less like a real event. Okay, so what I'm trying to showcase right here is to trace the origin of Poisson distribution back to binomial. Okay, so I'm going to go to page 12 right now. And of course, I'm actually going to stop at page 12 for today. Okay, now take a look at page 12. Okay, in page 12, we want to talk about cancer in a large population. The incident of cancer, occurrence of cancer is a rare event. Okay, it's a rare event. Okay, in a large population, particularly in the last city, this city in 1990, only 30 cases of cancer was observed. Okay, we can actually use a Poisson distribution to determine the probability that the number of cases of cancer is actually going to be 30. Okay, what am I trying to do right now? I'm trying to use the formula right here where the formula for Poisson, exponential raised to power minus lambda, lambda raised to power x over x factorial. What I'm trying to do now, I'm plugging my x equal to 30. Okay, x equal to 30, that is what I'm trying to do right here. If I want to figure out that probability right now, then I need lambda. What is my lambda? My lambda in this case, I call my lambda intensity parameter the other time. And of course, this lambda is an incidence rate. This lambda here is actually going to be a yearly average number of cases of esophageal cancer. Okay, take a look at that. That is what it's actually going to be. Okay, so like I said, I'm actually going to stop at, page, I'm going to stop at page 12 today. And of course, tomorrow, I'm actually going to start at page 13. Let me tell you this material right here is actually, this way I'm actually going to start from tomorrow. Okay. This material is what we're going to use for the entire week, for this week. Okay, Now, is there anyone who want to ask question? Is there anyone who need clarification? Is there anyone?
I have a question, but it's unrelated to the lecture material.
Okay, go ahead.
So I had been emailing you the last couple weeks about a midterm question that you or someone regraded, but it was regraded incorrectly. At least I think it was. And I just wanted to ask you in class if there was a status update on that, or if I can show you the lecture video where we were given a formula to find the answer for this question.
Okay, you are very correct. You know, what I'm actually going to do is this. If I hear you correctly, you are actually talking about a particular question in the meantime too that I regraded that you think probably maybe regraded incorrectly. Now, you know, this is what I want to do. I'm actually going to finish my lecture this week. And of course, I want to attend to all concerns next week. And next week, I'm actually going to use next week for office hours. I'm planning to use 3 days for office